Welcome to This Explainer. I'm absolutely thrilled to share today's topic with you because we're looking at a breakthrough that fundamentally changes how we make artificial intelligence smarter. Up until now, if you wanted to significantly upgrade an AI model's capability on a complex task, you usually had to retrain it, fine-tune its internal weights, or rely on incredibly messy, bloated prompts. But what if there was a cutting-edge method to systematically upgrade an AI's intelligence without touching a single line of its core code or paying massive computational costs, which, as we know, can be completely financially crippling for large-scale enterprise deployments? Today, we're exploring a fascinating new framework called SkillOpt, developed by researchers at Microsoft, that does exactly that. So let's dive right into this paradox. Frontier language models, the really powerful ones we use today, are often closed, proprietary systems. Their internal weights or their brains are completely frozen to us. We can't just go in and fine-tune them. So the massive challenge in the field has been, how do we adapt these frozen models to become experts at highly specific, multi-step tasks when we're entirely locked out of their internal architecture? Now, I've got to tease this staggering number right out of the gate, just so you know the sheer scale of what we're talking about. 23.5. That is the average performance lift, in absolute percentage points, achieved on GPT 5.5 across 6 completely different benchmarks simply by applying the methodology we're about to explore. It didn't change a single weight in GPT 5.5, it just changed how it was instructed. To understand how we get that massive jump, we first need to define a skill document. Instead of relying on a human to write a quick prompt, SkillOpt relies on a persistent, optimized text file. You can basically think of this skill document as the AI's highly refined resume or its standard operating procedure. Before the AI executes a task, it reads this document, which is packed with specific procedures, tool policies, output constraints, and, importantly, historical failure modes to avoid. Including those failure modes is absolutely crucial because language models often suffer from a sort of amnesia, repeating the exact same silly mistakes over and over. By externalizing those failures into the document, the AI remembers what not to do, acting as an external memory of how to do a job perfectly. And this brilliantly illustrates the core dynamic of the entire SkillOpt framework. You've got two distinct entities working together. The snowflake represents our target agent, the model actually executing the task. It's completely frozen. It just reads the skill document and does the work. On the other side, we have the fire, a separate hot optimizer model. This model's entire job is to sit offline, review the frozen agent's successes and failures, and ruthlessly tweak and upgrade that skill document. Section 1. The deep learning analogy. So, how exactly does the hot optimizer know what to change in the text? Well, it takes the rigorous mathematical discipline of deep learning and applies it entirely to natural language. And this mapping isn't just a cute metaphor, it is completely operational. In traditional deep learning, you optimize parameters. Here, the text of the skill document is the parameter. Instead of a gradient direction telling the model how to adjust weights, the optimizer looks at execution trajectories to figure out how to edit the text. Instead of a learning rate controlling the math, we have a strict edit budget controlling how many words can be changed. We are treating text space optimization with the exact same strict discipline as weight space optimization. And you can see why that discipline is so absolutely crucial. If you just let an AI rewrite its own instructions without any rules, it makes massive, unpredictable semantic leaps, often erasing good instructions just to fix one minor bug. But by moving in bounded skill edits, controlled tightly by that learning rate or edit budget, the optimizer avoids those unstable jumps. It walks smoothly down the optimization landscape, ensuring that every new version of the skill document is an incremental, stable improvement over the last. Section 2. Inside the SkillOpt pipeline. In practice, the hot optimizer acts a lot less like a creative writer and way more like a strict, uncompromising manager ruthlessly editing the AI's standard operating procedure. The process is intensely systematic. First, we roll out batches of tasks for the frozen agent to attempt using the current skill document. Second, the optimizer model reflects on a mini batch of the results, specifically looking for recurring procedural errors, not just one-off mistakes. Third, it proposes bounded edits, literally add, delete, or replace commands for specific lines in the text file. And finally, step 4, those edits must pass an incredibly strict validation gate. If the new skill document doesn't definitively score higher on a held-out test set, the edits are instantly thrown out. When we look at the complete architecture, there's a really clever feature I want to point out, the rejected edit buffer. When that strict validation gate rejects a bad edit, the system doesn't just forget about it. It actually saves those failed text edits as negative feedback. So, in the next round of reflection, the optimizer looks at the buffer and knows,
Okay, I already tried telling the agent to do X and it made performance worse, so I definitely won't propose that again. This allows the system to learn from its mistakes without adding a single second of compute time when the final model is actually deployed.
Section 3. Unpacking the massive gains. So what actually happens when you run this strict, text-based training loop? Does writing a better instruction manual really rival changing the actual code of the AI? Well, here's that staggering number again, now with the full context. On GPT 5.5, operating in direct chat mode, SkillOpt lifted the average accuracy across 6 totally different benchmarks, ranging from math to multimodal document reasoning, by 23.5 points over having no skill document. It didn't just beat the baseline, it significantly outperformed expert human-written prompts and other automated prompt evolution methods. Take Spreadsheet Bench, for example. This is a highly procedural task involving complex Excel manipulation and Python coding. Without a skill document, GPT 5.5 scored a 41.8. With the SkillOpt-generated document, the score nearly doubled to an incredible 80.7. And I'll say it again, this happened without updating a single weight in the AI's brain. The intelligence was purely injected through optimal text. Now, you might be thinking this requires a massive encyclopedic prompt that costs a fortune to run. But no way. It's wild to think that these massive gains didn't come from bloated, infinite prompts. The final deployed skill documents were hyper-compact, ranging from just 300 to 2,000 tokens long. Even more shocking, these final documents were achieved in only 1 to 4 accepted edits. The validation gate is so strict that it rejects almost everything, only letting through the absolute most potent, high-value text changes. To give you a sense of what actually survives that struct filter, take a look at this learned rule the optimizer wrote and inserted for that Spreadsheet Bench task. Inspect workbook structure and formulas, then write evaluated static values across the full requested target range instead of relying on Excel recalculation. This isn't just a generic pep talk telling the AI to think step by step. It proves the optimizer learned deep, reusable procedural logic and specific domain heuristics, not just memorized answers. Section 4. The transferable AI superpower. Because the logic it learns is so procedural and fundamental, it unlocks something truly incredible for real-world application, the superpower of transferability. Because the skill is just a highly optimized text artifact, literally a simple markdown file, you can decouple the training from the deployment. You can use your most massive, expensive model offline to do the heavy lifting of optimizing the text. Then, you can simply take that text file and plug it straight into a tiny, cheap model like GPT 5.4 Nano. You get the procedural wisdom of a massive system at a fraction of the inference cost, instantly upgrading the tiny model's performance. And it goes even further than just moving between model sizes. It literally works across completely different execution environments from entirely different companies. Moving a skill trained inside the OpenAI Codex environment directly over to the Claude code harness yielded a massive 59.7-point gain on the Claude baseline. The text document acts as a universally readable, low-cost, incredibly powerful domain adaptation layer. By bringing this strict discipline of deep learning into the realm of natural language, SkillOpt proves that the way we instruct AI is just as optimizable as the AI itself. But it does leave us with a fascinating, slightly unsettling question. If an AI system can now systematically analyze its own failures, propose bounded edits, and rewrite its own instruction manuals to become vastly smarter, what stops it from eventually rewriting everything else? I'll leave you with that provocative thought as we wrap up this explainer on the incredible potential of text space optimization. Keep learning, and I'll catch you on the next one.